Okay, so let us continue with our lecture on this prolet spheroidal wave functions. Um, the main idea behind this huge discovery of this prolet spheroidal wave function is basically to connect certain problems in signal analysis. Actually, the characteristics of Fourier transform, like more fundamentally. So. It was indeed like, of course I cannot go through all the proofs. For example, the orthonormality proof, etc., I had to skip because those proofs are really big in terms of analysis. And moreover, when I talked about uncertainty principle, that uncertainty principle is also not very general, because I took the only easiest proof where I wanted to show that the spread or concentration problem of signal and its Fourier transform both cannot be done indefinitely. So when you have a signal, some signal, this is in time, and you take its Fourier transform, then we understand that you cannot concentrate both the signals indefinitely. So if you want to concentrate this in time, you will see that in the frequency there will be huge spillover. So we have seen it in like typical problems. For example, when you take a signal like a box function, a rectangular function, then we know that if you take Fourier transform, you will get the sign C, the cardinal signs. So the problem with cardinal sign is that you have seen the earlier video lectures on Fourier transform and all, that they are definitely not bounded in frequency. So they are not at all band limited, because here the signal, original signal, is time limited. So it is going into infinity in both the directions. Moreover, these functions are having some like sin C function is not a very ideal function in terms of concentration. Not only concentration, suppose L1 characteristics, this sin C function is not even L1. So if you integrate the absolute of sin C say t dt, that diverges, that goes to infinity. So that is one problem. That's why the inverse Fourier transform of such function, normally that does not exist. But if you approach from the L2 theory point of view, from this Plancherel's theory point of view, you will see that you will get, definitely you will get the box function back if you take the inverse Fourier transform, but that Fourier transform will not be continuous. The inverse Fourier transform will not be continuous, so which is evident from the box function. Now we can approach this Fourier transform. We can take some more examples. For example, one is Gaussian. So if you take a Gaussian pulse in time, we know that the Fourier transform will also be Gaussian, because this is the so-called eigenfunction of Fourier transform. But if you decrease the variance of the Gaussian kernel here, like if you make the variance smaller and smaller, you will see in the Fourier transform that will be larger and larger. So in the limit, we know that when we talk about distributions and all, so we know that these two functions, say the constant function, so a constant function, say this is a time, so we say that xt is equal to some constant a. We know that if you take the Fourier transform, of course this is not a L1 function, this is a L infinity function, but however, if we can take the generalized functions into consideration, for example those Dirac delta, we know that for such a function the Fourier transform will be Dirac delta. So this is another example of showing that how the concentration or spread problem is having this uncertainty principle in it. For example, this Dirac delta function is infinitely concentrated. So the entire energy lies on that singular point. However, the corresponding transform domain, it is having infinite spread. So it is having the same power on the entire real line. So these are some problems. Now, if you look at the second paper of this prolet spheroidal set, they basically developed some curious results on uncertainty principle and basically generalization of the uncertainty principle, because when I talk about the uncertainty principle in the Heisenberg sense, then the form is W into basically the spread D in time into the spread in frequency is greater than or equal to half. Now suppose I want to understand that this spread is just like the time duration. It is not actually, but some practical time duration, if I say about time limitation, some practical, that there will be some signal outside that interval, that D interval, but that will be having very less energy. So this D is some practical time duration, and this is some practical bandwidth. And this kind of practical bandwidth is used in filter theory also, like 3 dB bandwidth, etc. When the power drops below 50%, you say that to be the bandwidth. So this is some practical bandwidth. Then you can see that what does this D into D greater than or equal to half means. So essentially, when I am talking about some 2WT theorem, so over there I am basically trying to say that 2 into the time duration D into the bandwidth capital D is greater than or equal to half, or basically we are trying to say that the signal is at least one dimensional. That makes sense, right? One dimensional. That makes sense. However, this particular uncertainty principle, this inequality is very loose. I should say this bound is very loose. We need tighter bound. We need restriction on this concentration in a much better way. However, like our classical uncertainty principle or Heisenberg's uncertainty principle, that does not give that. This is pretty loose bound. So this second paper on Prolet spheroidal wave function, they developed some methodology to have stricter bounds, and basically they used the so-called eigenvalues of those Prolet spheroidal wave functions, and those eigenvalues lambda 0 to lambda n and so on. So using them, they put some nicer bounds on these spread of time and frequency, the signal energy spread on time and frequency, and those results I'm not mentioning them because that will be too much for this course, but those results are much more tighter, and it will have a larger value of this over which you are basically binding the time duration and bandwidth. Now moving there to the third paper, because the third paper is more interesting. In the second paper is required to prove the third paper, but we are skipping some rigorous proofs altogether, so we can straight away move to the third paper because that is where our interest lies. Our interest lies in this dimension, like what will be the dimension of a signal which is having some approximately, which is approximately band limited and which is approximately time limited. So let us move towards that approximate time limitation and approximate band limitation problem. And approximate band limitation problem. So since I'm talking about this communication problem specifically because there can be different kind of options. For example, you can take time limitation more strict than band limitation, or you can relax both the case. But in communication problem, we know that the band limitation is stricter, so we cannot move to other region outside my specified band. So we assume that we have a signal which is band limited with bandwidth minus omega to omega. This is stricter. My signal has to reside within this. So we say that so we define the spaces to be B omega to be the space where you have your signal reside there, and Fourier transform of ft is basically the support of Fourier transform of ft. Support of Fourier transform of ft is minus omega to omega. This is my band limited signal space, and my signal resides there. Now we know that we cannot have time limitation like of such signal, since the intersection between these two spaces is essentially the trivial signal 0. You cannot have any meaningful signal here. So what we can do, we say that we define a new space. We define a new space which we are naming to be E epsilon t. So this space is defined to be that this space is a subspace of B. This is a subspace of B, and this we are defining to be E epsilon t is space of such function ft belonging to B such that if you apply the time limitation operator of on that, the time limitation with duration capital T on that, then that energy will be the maximum energy loss will be basically epsilon t square. So if I take the energy, that energy will be this energy will be 1 minus epsilon t square. So we say that you have epsilon t square, that amount of energy which is lost in the process of time truncation. So you have the signal, this is the band limited signal, and when you are truncating in time between minus t by 2 and t by 2, you know that some energy is lost which is outside that time region, and that loss of energy is epsilon t square, that fraction. We are assuming that the signal is having unit norm, okay, without loss of any generality. So we are using unit norm signal. This is equal to 1 unit energy signal. Okay. So in this space, this is definitely like subspace of this band limited signal space. Now what we want to do, we want to have some expansion of this space, and we want to see that how far this signal, how far this space is from the time limited signal space, and how far is this space from like a finite space, with some basis function. So these questions we want to ask. So let us draw some diagram. So let us assume that this is a space of L2 functions in general. Okay. So what I want to see, so out of this L2 space, there are some spaces. For example, one is say band limited signal space B. This is a subspace. We have the so-called time limited signal space as well, which is say DT, and they are intersecting only in the trivial 0 signal, nowhere else. Now out of this space, I am taking another subspace, which is this EET space, E epsilon t space. Okay, that is again a special subspace of this. Now what I want to show that this particular signal which I am defining, or this space E epsilon t, this is approximately finite dimensional space. This EET, which will be our space of digital communication signals, this is approximately finite dimensional space. And that dimension is my 2WT. So that dimension is approximately 2WT. So how to make sense? What kind of mathematical truth is there in this approximately statement? That we want to show first. So how do you like find out dimension of a particular signal? So let us start with any random any particular signal. So if I say about dimension, take any signal f in L2 say, then we know that for any signal f we can have if there exists some orthonormal basis function. Suppose there is some orthonormal basis function, say phi n for n is equal to say 0 to infinity, then we know that we can write down that function in terms of a Fourier series, which is written as this fn. So this is the Fourier series expansion, and we have already seen a couple of Fourier series expressions till now. So one is using the complex exponential as a basis function for like time limited signal or periodic signal. We have seen the sampling theorem for band limited signal. We have seen the Prolet spheroidal expansion as well. Now, what is the dimension of such signal? As it is going to infinity, this is an infinite dimensional signal. So you can visualize it. So this is suppose a vector phi 0, this is an orthogonal vector phi 1, another orthogonal vector phi 2, another orthogonal vector. So the dimension increases. This is 2 dimension. When you increase another dimension, say phi 2, this will be 3 dimensional. If you increase another dimension by phi 3, that will be 4 dimensional. So it increases, and as you go to infinity, it will become infinite dimension. So it will become finite dimension if only I can write f by a Fourier series where this n is equal to 0 to infinity does not go to infinity, it goes to some finite constant, say capital N. So if I can write f is equal to say n is equal to 0 to capital N using some basis function, then we can say that this particular function f is finite dimensional. With dimension n plus 1, or here I can write n minus 1, so with dimension n. But that is not possible for general L2, definitely not possible. That is not possible for time limited only function, also not possible. That we have seen, because Fourier series it does not truncate at any point. That is not possible for only band limited, because that we have seen from sampling that it goes to infinity. However, in this particular space, so we have seen that like B is not finite dimensional, D is also not finite dimensional, L2 is definitely not finite dimensional. But our this function space epsilon et, which is a subspace of B, that is approximately finite dimensional. So in what sense? Why approximately? Because it will not be exactly equal to, it will be closer to some finite dimensional Fourier series in some sense. So in energy sense, so what do we want to say? That we will get the finite dimensional expansion where the error energy will be arbitrarily small. That is the understanding. So what do we want to do? I want to compute the energy between the signal and some finite dimensional Fourier series, n is equal to say 0 to n minus 1, and you take the 2 norm of that. So this is the error energy, this is essentially the error energy. Now you want to see that this thing, the like maximum of such energy, error energy, it goes below some pre-specified arbitrarily small number, some delta. So if we can enforce that, and then only we will know that this particular signal f will be approximately finite dimensional. So to solve this problem, how this approach has been made, that I will discuss. But of course, I will not discuss the proof in entirety. That is that will be beyond the derivation. I actually read the entire paper. That paper is some 40 page long. I can share with you, but after some time, you will see that the things will go beyond our scope. It will be too analytic, and there are some like some step jumps as well. So it requires some other lemmas, other theorems, so which will be too much in this course. So I thought a lot actually in during last 2 weeks that how to represent it, how to present it. So I'm teaching this for the first time. So this is not the best, I guess, but I don't know. So let us try to present it in a particular way. Hopefully we can improve on that. I'll see if I can give a better proof in future if I get something from some other paper, because this is the first paper where the proof is pretty rigorous, pretty big. Okay, so the idea behind this approach is, so when they started investigating what they want to have something like this, they had some conviction that for some finite dimension n, this thing is true, and this delta, it does not depend on any of the choice of the dimension or the choice of the basis function, etc. This is arbitrary. This is arbitrary. As long as your signal dTf, that energy is equal to 1 minus epsilon t square. This epsilon is some small value. Then this is true. So how to if I want to prove something like this, how to approach? What kind of difficulty we face that we want to see. So first let us talk about this Fourier series. Let us talk about this choice of basis function and the so-called inner products. These are some coefficients, right? So I can if I don't know the basis, this is basically some complex coefficients or real coefficients. So if you are basically this sum is nothing but linear combination of these basis functions. So whatever basis functions you are having, you are taking a span of that. You are taking some arbitrary linear combination. Now this inner product is eventually come from this orthonormality and all, but generally speaking, like we can have from linear algebra, we know that this is good enough to write some an phi n. Okay, n phi n t, I can say n is equal to 0 to n minus 1, and this is less than some delta. This is essentially the span of the n-dimensional span of the n basis functions, some arbitrary linear combination. So we can set the optimization problem from here. So let us assume that within that space of band limited signal, this is the band limited signal space, and within that you have a finite dimensional space which I am naming to be some S phi n. S phi n is basically the span of phi's phi n for n is equal to 0 to n minus 1. This is this space, which can be written as all the functions of this form a n phi n is equal to 0 to n minus 1, where n's are scalars. So they are real or complex depending on what problem we are solving. So this space, this is a finite dimensional space, S phi n, suppose. This is a finite dimensional space. Now you have a signal which is f, which belongs to, suppose that E epsilon t. This is another space. Okay. E epsilon t and there can be overlap, there may not be overlap, I don't know. So right now I am not drawing it, but there it is possible there can be some overlap. Okay. Now what I want to do, I want to see the distance from this function f to this finite dimensional space. So that distance, if you take any arbitrary linear combination like this, those arbitrary linear combinations can be anywhere. So if I want to minimize the distance between f and this linear combination, we know that this linear combination, this will be minimum. So if I minimize for all n, all an between 0 and n minus 1, we know that this will be minimum if I compute the orthogonal distance. If I orthogonally project f from here to this finite dimensional space, then whatever is left, whatever distance you are getting, that will be the minimum distance. So initially find out the minimum distance. So this minimum is basically saying that you have to do some finite Fourier series expansion over n is equal to 0 to n minus 1. So this is the first optimization you want to do. And that will give you the orthogonal distance, the orthogonal projection, and then the distance. This is the error. This is the error actually. Next, you don't know, you want to like this one I can say to be I can name it to be some distance rho between f and the space S and phi. So this is the minimum distance, this we can say. Now this f can be arbitrary, f can be any function inside this space E epsilon t. So I want to maximize such minimum distance over this entire space of E epsilon t, which we will name to be the deflection. So deflection between the two spaces, E epsilon t and S n phi. So this space is the so-called band limited but approximately time limited space, which is our digital communication signal space, but approximately time limited signal space. And this is my finite dimensional space, n dimensional space. So deflection is basically the maximum distance possible between this and this. So I can take another symbol, say delta n, which is equal to basically the max or sup. I am writing max. So max for all f in that space, and I am computing the distance between f and S and phi. So this is delta n, I can write phi or something. When you are choosing phi to be the basis function, I can write like this. So this problem, essentially you are choosing any f and you choose the orthogonal distance and orthogonal distance, and you see out of these distances whatever is the maximum. So that is called the deflection between these two spaces. Now what I want to do, I want to minimize this deflection. So my objective is that this deflection, which is essentially a sense of how far this so-called band limited and approximately time limited signal space from a finite dimensional space. So that I obtain for a particular set of basis function for this particular S and phi. My last optimization will be to find out the basis function for which this deflection is minimized. Now listen carefully. So till now I have shown you two levels of optimization. First level is so-called Fourier level optimization, where you are choosing the coefficient, the linear coefficients for the linear combination, and that basically gives you the Fourier. Second one, you are choosing for arbitrary functions in that particular infinite dimensional space to get the deflection between the two spaces. Thirdly, I choose the basis. So this is first level, this is second level, and now I am moving to the third level. Third level is choosing the subspace S and phi, or basically choosing the phi. So which basis to choose? You have to choose only n basis, n orthogonal basis, n orthonormal basis. So there are infinite ways of choosing those n orthonormal basis. Which orthonormal basis is to choose? So you basically vary this space. So I can schematically draw that basically you have to vary this space. So there is a variation here, this s and phi, you vary the phi and then measure the distance, the deflection from epsilon t, whatever be the deflection, the max of the distance. So deflection I am saying delta n phi or something, delta n phi. So find out the minimum such deflection by choosing different phi's. So the last one is basically I can say that you have to minimize that deflection in phi for different phi's. So your like phi will come out to be the argument of this minimization problem. So this is essentially this triple optimization problem, I can say. The first minimum, this is the third minimum for 0 to n minus 1, then the maximum for all f, then the first minimum for all an, and then you are minimizing f minus summation an phi n is equal to 0 to n minus 1 square. And if you solve this particular triple optimization problem, what you will get? You will get some basis. So after solving this triple optimization problem, you get some finite basis only if this value, only if this mean of delta phi n for all phi for all possible phi is less than some pre-specified delta. So if this is satisfied, then only we can say that these bases are this finite set of bases will approximately we approximate this space E epsilon t. So oh, not only that, so this will tell you that the basis is at most capital N. The dimension is at most capital N. We have to show that it is not less. We have to show that if you take, instead of n functions, n basis functions, if you take say n minus 1 basis functions, then you cannot minimize this particular quantity. You cannot bound this error by some upper bound. Rather, you will get some lower bound of such error such that it cannot arbitrarily be smaller, arbitrarily make smaller the error energy. So you will ensure that the dimension is actually n. So mathematically we can write those statements in precise form, that if you get such basis function. Now before going there, I'm just stating the third serendipity. Why third? The first one is that for this band limitation, eigen limitation, band limitation, time limitation operation, the operation BD, the Prolet spheroidal wave functions are eigen functions of such operation of that finite Fourier transform. That is the first serendipity. Second serendipity is basically that the Prolet spheroidal wave functions can be used to tighten the uncertainty principle. The third one is this, that after solving this optimization problem, which is pretty long, I'm skipping it, the solution which you get is basically the first n Prolet spheroidal wave function. So the solution after solving this optimization problem, you get that those phi n's are basically psi 0, psi 1 to psi n minus 1. So these set of basis functions which are orthonormal, we know. So these n basis functions, capital N basis functions, indeed solve the above triple optimization problem. No other function. So if so, proof in that third paper, but I am skipping it. So if they are the optimization, they are the basis function, those product spheroidal wave functions are the basis functions, then we can clearly see that the approximation is basically this, some 0 to some n minus 1, and these are some an psi n. Okay, these are the product spheroidal wave functions. Now what is this n? The second question which will be asked, that what will be that n? Okay, fine, these are the basis functions and I am solving this, so I know that the n dimension, the so-called n dimensional space is n psi, I can say s n psi, over which I am projecting that function from e epsilon t. So this function belongs to e epsilon t, and that I am projecting, suppose here, and this distance is the minimum. This distance is not only the minimum, we can say that this is less than some arbitrary delta value. So this f minus, this is approximated, f minus this an psi n, 0 to n minus 1, this energy is less than some delta, some pre-specified delta, which can be shown to be having this value approximately equal to, I can say like less than, I can say less than some 12 epsilon t square. So it depends on the same small energy value which is there in the time limitation process, and this 12 is a constant. So as you take epsilon t tending to 0, we will see that this goes to 0 as well. Now this is true for what value of n? For which value of n? So this gives the second curious result, that this n is equal to 2wt, the ceiling, the integer greater than or equal to. So this is remarkable. That proof is also there, but not only this, it is not less than this 2wt, that is also true. So the second theorem which is proved is this, f minus an phi n, if you go anything below that, say if you go less than n minus 1, say n minus 2, for n is equal to this, then that is not less than something, rather that is greater than something, that is greater than some constant into epsilon t square minus some other function, So we know clearly that if you go one dimensional below this n, this 2wt, you cannot actually approximate such signal using a linear combination of n minus 1 basis functions. This is not true. So it is arbitrarily like it is greater than some constant, and so you cannot make them come close in energy in L2 norm arbitrarily. So that enforces that the signal is indeed 2wt dimensional. Approximately, yes, but this is 2wt dimensional. So I can go on for a long time with this, but we have to move elsewhere. So once we are convinced, we understand that I did not prove, but I'm like the proof is there in that third paper. I can share it if you want to have a look. So if we have 2wt dimensional signal, then finite dimensional signal will be easier to analyze, and now I'm going to something called the number of such signals, such finite dimensional signals which are possible under a noisy environment or a finite precision environment. So this will be the idea towards Kolmogorov's epsilon entropy. But before going there, I want to mention another thing. Yeah, in typical digital communication books, this actual method is not given because of its difficulty. Definitely, there are some like intuitive proofs are given of this 2WT theorem, the so-called Fox theorem, which people used to think. And these hand-waving arguments were given in 1930s, 40s books. Even in many of the standard textbook they are given. So although they are not correct, but nevertheless I should mention them. So the first idea of this 2WT can be brought from Fourier series, and the second way can be brought from sampling. So from Fourier series, what we can understand that if the signal is indeed having time duration t, suppose uncertainty principle is wrong, so exactly t, there is no spillover, then we know that for a signal having this duration t minus t by 2 to t by 2, suppose, we can have a Fourier series expansion. So if I do Fourier series expansion, what will be the fundamental frequency? The fundamental frequency will be 1 by t. So the fundamental frequency is 1 by t. So how many harmonics will be there within the W bandwidth? So the number of harmonics will be W, that is the bandwidth, divided by the fundamental frequency 1 by t. So yeah, you can put a ceiling. So that is equal to WT. So there will be WT coefficients, and we know that every coefficient is a complex coefficient, so there are 2 degrees of freedom for every coefficient, so the total number of degrees of freedom is 2WT. So that is the number of dimension which a signal can have. You can take the sampling route as well. Again, forget uncertainty principle. Then if your signal is band limited, having bandwidth W, then we know that Nyquist sampling theorem says that with 2W samples per second you can sample it. So per second you are having 2W symbols, 2W samples. And what is the time duration? Time duration is t. So there are total time t. So how many samples are possible in t time duration? 2W into t. So that is the total number of samples possible of that signal. So again, this is a kind of dimension or degrees of freedom. However, both of these proofs are not correct because like the assumption that when you are saying that you can take Fourier series is wrong. The signal is not time limited. Here also, when you are saying that you are taking only 2WT samples within this interval, that is again wrong. The signal is not time limited. So from there I am leaving you because the precise formulation is through this, through that triple optimization, and then trying to find out that what n will satisfy such delta, and from there they obtained that this value 2WT. So that is coming from a series. In that paper it is there. Okay. Now let us move towards our actual objective, which is the counting the number of such signals possible in that particular space. So our space is now S n psi, right? I was writing like this, S n psi. So these are my Prolet-Spheroidal wave functions. N is n dimension. So this space we can try to find out that. So what we obtained that this is a finite dimensional space. That's fine. Till now we obtained that this is a finite dimensional space, but still, how many signals are possible in this space? How many vectors are there? That is infinite till now. In the next step, we want to show that not only this is finite dimensional space, rather this is a finite space. This is a finite set. So there are only finitely many vectors possible in this space under certain realistic assumptions. So realistic assumptions means the assumptions which will make only two. One is the signal is having finite energy, which is obvious. So these are L2 signals. So it is having some finite energy. This is a subspace of L2. And I assume that the maximum like energy of such signal is say some E. Okay, that is the maximum energy. Second is having finite precision. We should talk a little bit about this finite precision. Suppose there is some precision, some epsilon. Epsilon is the precision. So what do you mean by precision? Precision means that how clearly I can observe a particular signal, how uniquely I can observe a particular signal. So suppose you have a signal, say sine, a nice sine waveform, and I have another signal which is almost there. Now if you are observing these two signals, if I ask you that are they different signals, how do you know? How can you compute? So what you can do, you can do sampling. You can do a particular sampling at a particular point, and if you see that the two samples which are coming from the two signals are different, then you can say okay, they are different. Or you can do some Fourier series and you can compare every coefficient case by case and then say whether they are same or different. So for one signal, suppose f, the Fourier series is say a n to the power in omega t, and the second one is say summation bn e to the power I n omega t, and then you can compare every an and bn. So you compare a0 with b0, you compare a1 with b1, and you see. So if you find anything which is not equal, then you will say they are different. But when you are comparing two real numbers or two complex numbers, how close you can go? If I ask you that are 3.14159265 and pi are same or different, you will say different, yes, because pi is not really a rational number, it does not stop. But if you approach it, if you move forward with the sequence, say after the decimal point you go up to say 100 points, and if I ask you that are they same or different, definitely they are different. But when we can use this rational number as a good approximation of pi, that depends on your like problem what you are working on. So for our regular engineering applications, say 3.14 is good enough. For some high precision applications, we can go up to say 10 decimal points, like 10 numbers after the decimal point, or you can go up to 100. It depends on what application you are doing. So approximation, they are not equal, but they are practically equal. So this practically equal thing we have to be very careful about, and this is called the precision, that whether they are practically equal. So whether a0 and b0 are practically equal, whether a1 and b1 are practically equal, then you can say whether this signal f and g are practically equal. Now this is one thing is choice, another thing is your measurement capability. So by which you do measurement, you will measure different quantities like length, time, weight, etc. by some instrument. So measuring instrument, so for length, suppose you are measuring using a finite scale. So that scale, by your eye you cannot distinguish a micron range. So if something is say 1.43 millimeter, and if something is 1.44 millimeter, it will be very difficult to distinguish these two by just your eyes. So you can have a slide calipers, you can have, and then you can move towards microscopy to like distinguish two signals, two measurements which are close enough. So better and better measurements are required to distinguish between very close measurements. So that is what we say, that increasing the precision. But can this precision be increased arbitrarily? Can this be infinite precision, like infinite similarly precise instrument? That is not possible. So your physics is having limit, your instrumentation is having limit. So when you talk about signals, when you do this spectral analysis, this Fourier analysis, you are basically passing it through a like bank of correlators and filters, and you are measuring that what coefficient is there with respect to a particular harmonic. And that measurement, when you are taking the value, that value is basically some amplitude and some phase, which is a complex number. So that amplitude and that phase, that you cannot measure with infinite precision. So there is some finite precision. So this precision thing, and let us assume that they are having epsilon precision. So we say that something is having epsilon precision. It means that if you take two signals, f and g, and if their error energy is less than epsilon, then we say f is equal to g. They are indistinguishable. This is what the meaning of precision is, that if the error energy between the two signals is less than some epsilon, we will say that they are indistinguishable. Okay, so in that vector space, we can draw it now. So this is a finite dimensional vector space, so I can draw it in this way as well. So some finite dimensional vector space. So f is a vector. These bases are basically those psi 0, psi 1, psi 2, 2 psi n, etc., psi n minus 1, like that. So f is a vector, and this f is having some energy, some finite energy, and g is another vector. So we say that f minus g's energy, which is basically this, if that energy is less than some epsilon, then we will say that f and g are indistinguishable. They are same. So this is what finite precision means. So we can say clearly that in this space, if you take a small ball of radius epsilon, this is like a n-dimensional, capital N-dimensional ball of radius epsilon. So within this ball, you can uniquely identify only one vector, only one function. Because if you take, suppose this is a function, and if you take any other function that will be closer to epsilon, so then we will say that they are indistinguishable. Oh, okay. You can say that, okay, there are two signals inside this which are having more than epsilon, so I can put it epsilon by 2 or something like that, or less than 2 epsilon. That's fine. That does not change anything. It is small only. So if it is less than some 2 epsilon, we will say that they are indistinguishable. So we can make a ball of radius epsilon. Length is energy in Hilbert space, in L2 space. So if you define a ball like this with radius epsilon, then we say that any two signals within that ball will be indistinguishable. They are same. They are within that precision limit. So clearly, like, this entire volume is given to a single signal. That one signal is uniquely identified within this ball. Okay. So precision gives us this enormous like understanding that in reality, within this epsilon energy ball, there are how many signals possible? Uncountably infinite number of signals possible. Every point is a different signal. But we say, since our measuring instrument is having some finite precision, we cannot really distinguish between them. For us, all of them are same. You have to go at least this 2 epsilon apart to get distinguishable. Then they will be different. Okay. Now we come to the final cool concept of epsilon entropy. So under these two assumptions, finite energy and finite precision, So in a finite dimensional space, so this is our finite dimensional space, psi 0, psi 0, psi 1, psi 2, 2, psi n minus 1. In this space, I draw a sphere. Why this sphere? Because this sphere is my space of finite energy. The radius is, say, E. Okay. The radius is, say, E. So all my functions which are which belongs to this particular space, this space Sn psi, and having finite energy E, root E. Yeah. Energy is E, so the radius is root E, which is basically the square root of the norm. Square root of the energy. Norm is root E. So every signal will belong to this sphere. So what is the volume of this sphere? We know this will be some constant k into root E whole to the power n, which is 2Wt. Isn't it? That is the volume. Say V Sn phi. Sn psi. This k depends on the dimension. K is a constant which depends on dimension. We know that for dimension 1, k is 2. For dimension 2, so when dimension is 1, k is 2. When dimension is 2, k is 2 pi. When dimension is 3, k is 4 by 3 pi, etc. So this is a constant. Now within this sphere, we know that every distinguishable signal resides within a ball of radius. Radius is not epsilon, radius is basically root epsilon. So energy difference is epsilon. So resides a ball of radius epsilon, root epsilon, and within this ball one signal is like uniquely distinguishable. But if you have multiple signals, they are not distinguishable anymore. Okay. Now you get the idea. So one signal that resides within a ball of radius root epsilon. So what is the volume? So volume of that ball. So this is say V epsilon or something like that. This is equal to the same constant k, which is a constant for the dimension, into root over of epsilon to the power 2Wt ceiling. That is the volume. Now I ask you the question, how many signals are possible? Now it is clear that you can have a different signal if that other ball does not overlap. So you can basically do ball packing within this sphere. So how many different balls can be packed without overlapping? Because if you overlap, you cannot uniquely distinguish them anymore. They are different signals as long as there is no overlap. So how many number of signals possible? So that number, I can say some m is equal to, which is the number of the signals, is the volume of the entire space divided by the volume of the epsilon ball, which is k into root E whole to the power 2Wt divided by k into root epsilon whole to the power 2Wt. So that equal to, k cancels out, so E by epsilon whole to the power around WT. It's not exact, yeah. So I can say 2WT divided by 2. It is around 2WT divided by 2. That is the number of signals, and this is less than infinity. Obviously, this is finite because W is finite, T is finite, so dimension is finite, E is finite, epsilon is finite. Epsilon is not 0. Epsilon is finite. So this is finite. Finite to the power finite is finite. And this particular number is called the epsilon entropy, Kolmogorov's epsilon entropy, and this is the first instantiation of information theory, we can say, and it is in a very deterministic way. Till now we did not discuss anything random. Nothing is random till now. So all the signals are like deterministic signals. They are approximately band limited, approximately time limited. They are band limited and approximately time limited. They are having finite energy and they are having finite precision. Then we see that the number of such signals is finite, and it is called the Kolmogorov's epsilon entropy. So how many number of bits are required to represent such finite number of signals? Take logarithm. So number of bits required will be equal to approximately WT log E by epsilon. This particular expression will come back again. So after say 2 months we will talk about capacity. Over there in Gaussian channel we will see that this thing will come as a capacity, where this epsilon term, which is the precision, which will come from the noise, the additive white Gaussian noise, the so-called Bass spectral density, that value will come, and entire thing will be exactly same. So this is a very strong result, and this result, this particular result will motivate us that okay, since it is finite, then why do analog communication? Because analog communication talks about like uncountably infinite analog signal where time is continuous, the value is continuous. Then sampling tells us about like discrete, but discrete is also infinite because it is countably infinite. But what we find out? We find out that it is no longer countable, it is finite. The signal number is finite. So you can represent every signal using a bit representation with so many number of bits, WT log E by epsilon number of bits. So I can say that okay, fine, this signal is represented by 0000. This signal is represented by 0001. This signal is represented by 0010 if this value is say 4 or something. If it is 8, we have to increase. So this is the key behind digital communication. So on this note, I'll stop today. I know that the initial few lectures were like a little sparse. I could not take so many classes because I was reading the paper. I was thinking that how much I can go. Unfortunately, I could not go that far because the third paper is like 40-page paper. It took me 1 week to read it. But then I thought that okay, I'll give you the motivation. I'll give you the big problem. I'll give you the problem statement and how it was done. But exactly what has been done, I skipped. That is really beyond the reach in this semester, that triple optimization, etc. That is not possible within this limited scope. So understand up to this. I wanted to show you that this is a very significant result, and this you will not get anywhere. Like I'm teaching this subject for 5 years. This is the 5th year I'm teaching, but this is the first time I'm going like to the such depth that why digital communication? This fundamental question. Nobody actually answers that. In no book it is given. People say that okay, computational facility, like we can compute easily, digital hardware is cheap. Why digital hardware cheap? Why people actually did research on digital hardware? The motivation is here, that the signal itself is finite, so we don't need analog computation. That's why unless you are in some military application or very high power application where like your digital hardware cannot handle, or very high precision stuff. For all other things which are low precision, which are like low power, the number of signals are finite. That is why digital, nothing else. And that is why people give time and money to developing digital hardware. Okay, so I stopped today. Tomorrow I am starting another interesting thing. So this semester you understand that I am going in a non-traditional way. So I will be starting random process. So I talked with your analog communication professor who told that he did not get enough time for random process. So I will be giving you some brief overview of random process and some important theorems. So our second cast, so Shannon's idea of digital communication is that fine, it is finite. But now I will say that the signals are random. Even the message signals, the source signals, they are random. They are not deterministic. So that is a major departure from analog communication, because in analog communication, all signals are assumed, apart from noise, all the signals, the transmitted signal, those signals are assumed to be deterministic. Not here. So I'll start with random process tomorrow. And I'm not giving any assignment as of now. Let me complete the prerequisite stuff within the first month, like random process, and then the beginning of information theory. Okay, after that I will give you assignments, but give some time, listen to these lectures. I'll provide you some material, go through them, try to grow through them, at least appreciate the problem, what we are doing. Okay, bye.